Hello, this is Brian Washburn. I'd like to give an introduction to simple harmonic motion. Okay, so we've already talked about simple harmonic motion, but I'd like to talk about it, review it again, and talk about it a little bit more detail on the concept, using concept of mechanical energy. So you've been first introduced in simple harmonic motion is I have a mass spring system. I have a mass, there's no friction acting on it, and only horizontal force acting on is a spring force, or what we call Hooke's law. Hooke's law is the form of what I would call a linear restoring force. Okay, so it has the expression minus kx in the x hat direction. Okay, so first of all, the magnitude of the force depends linearly on the x, where x is the displacement of the spring respect to some equilibrium point. And then the force points in the opposite direction as the displacement, so in the minus x direction. Okay, so first of all, this is a linear force because it depends on x. It's also a restoring force because of the minus part here. Okay, and so what causes simple harmonic motion in any situation is a linear restoring force. That's really important. Now, since this is a conservative force, it's a conservative force because the force does not depend on velocity or time, and it just depends on position. I could define a potential energy using my definition integral, and the potential energy is 1/2 kx squared. Okay. Now, before I talk about the solutions, you may say, well, why is simple harmonic motion really important? I mean, we study it a lot. And you may say, well, why is it so important in a lot of physics problems? And the reason why is this. So say I have a more complicated problem. And here's an example. So I have some potential energy, some kind of funky potential. And it kind of does this, all right? And I want to solve for the equations of motion for that funky potential. Well, that could be a very complicated problem depending on the functional form of this, all right? However, I can always use a Taylor expansion. Okay, and I can always expand this guy into a series of Taylor series. And the first term might be something that looks like, I don't know, C or minus CR. And then there will be higher order terms. Okay, well, what that does, notice that is a linear restoring force. So then if I restrict my values of R, I can basically use that linear restoring force describe motion about an equilibrium point. Okay, so something like this. Okay, so then if I Taylor expand this, really I'm Taylor expanding this function about a R naught, because so this should be really R minus R naught, but I think you get the point. Then I have a linear restoring force, and then I've had the problem solved already. I know that, oh, it's simple harmonic motion. Okay, and then I can go about my business. This is very useful. It's used in a lot of different areas. Okay, here's an example. Say I shine light from a laser into a piece of glass. I can express the induced dipole moment, polarization of material, as a linear restoring force, and from that I can get analytic equations for the index of refraction and the absorption as a function of optical frequency. That's really powerful. So this is why we learn it in this class here. Okay. So let's go back. What's important is that, okay, now let's write down my differential equations. So this is my second order differential equation. I get the equation for simple harmonic motion. And solution to this, which we talked about by guessing, and we'll show another way of solving this, is that this is the solution to this are sines and cosines, or what I call harmonic functions. Like harmonic functions are sines and cosines. Okay. Now, what I want to do is I want to look at the energy of the system. Okay, so let's look more specifically at the mechanical energy of the system. And let me look at a specific case. So the specific case is going to be equal to initially I have initial position but zero speed. Okay. Now, if you want to write this in terms of what are my initial condition, my initial energy, notice that T. Just to remind you, T is equal to 1/2 mv squared. So since V is equal to 0 at times T equals 0, at T equals 0, the kinetic energy is equal to 0. Potential energy is equal to 1/2 my initial condition x naught squared. But the mechanical energy at that time is the total, it's just mechanical energy because T plus U is equal to E. Okay, now what I want to do is I want to write down mathematical expressions for kinetic and potential energy. I'm going to take the derivative of the solution, okay, and I'm going to get x dot. If I take x dot and shove it into here, what I'm going to get is 1/2 m v naught squared x naught squared sine squared. Now, one thing just to remind you is that to say that, well, omega naught squared is equal to k over m. And so m times omega naught squared is just going to be equal to k. So then what I'm going to get here, and I have a typo here which I will make go away, I'm going to get 1/2 k x naught squared sine squared. If I look at the potential energy, it's going to be 1/2 k x squared. I stick x into there, I get 1/2 k x naught squared cosine squared. Now what we're going to do is add this plus this, because that's the total mechanical energy. Notice there's a common factor of 1/2 k x naught squared. And then I get the quantity sine squared plus cosine squared, that's equal to 1. So the mechanical energy is a constant as a function of time. There's no time dependence here. And it's equal to the initial potential energy that we started off with this system. So that shows that a mass spring system or simple harmonic motion energy is conserved for that. Okay. Now, since energy is conserved, we can express the motion in a kind of unique plot called a phase space plot. And what I'm going to do is I want to look at the quantity. I wrote it here, but let me write this. I want to look at the quantity x dot divided by omega naught, quantity squared, plus x squared. I want to look at that quantity right there. Okay. Now remind you that the potential kinetic energy is equal to 1/2 mx dot squared, and the potential energy is equal to 1/2 k x squared. So what I'm going to do is I'm going to take x dot squared and solve it in terms of the kinetic energy. That's going to be 2t divided by m. I factor out this 1 over omega naught squared. X squared is equal to 2u divided by k. That's what I have here. Now remember, m times omega naught squared is equal to k. So that means there's a common factor of 2 divided by k. But that's t plus u. That's the total. That's the total mechanical energy. And so notice that this thing here, this quantity here, is equal to a constant. Well, if I make a plot of x on the x-axis and the quantity x dot divided by omega on the y-axis, this is the equation of a circle. Okay, this is the equation of a circle. A squared plus b squared equals the radius squared. Okay, and that's a real cool way of looking at the motion. Okay, so we're going to use these space plots to look at all kinds of oscillatory motion. Okay, and in fact, let's talk a little bit more about phase space plots. We'll use this to analyze the motion quite a bit. In fact, we're going to use it to analyze motion that's not simple harmonic motion. However, if the motion is periodic, the phase space plot will always be a closed shape. And so let me talk about some properties of the phase space plots. So say I get like an ellipse or some kind of closed funky shape. If it's closed, that means the motion repeats. Okay, and so if it's closed, it makes like an ellipse or some kind of football shape. That means that the motion is periodic, energy is conserved. Okay, but it doesn't mean it's harmonic, meaning that the solution x and x can be described as cosine or sine, sinusoidal functions, harmonic functions. Now, we're also going to get cases where there's a non-conservative force, and a good example is where I have oscillatory motion with dampening. In that case, the phase space, we can still plot a phase space plot, except what's going to happen is that the radius is going to change as a function of time. That means that energy is lost. So here in this particular case, this spiral thing here, I start off with 0 speed at some initial position, and then it oscillates and eventually goes, it goes to 0 and stops. Well, again, that is a behavior that is energy is not conserved. And then just like what we saw before, if the plot is a circle, then the motion is harmonic. All right. So let's take a look at a couple phase space plots. So here what I have is I'm using this simple pendulum differential equation solver that we've been using all along. And I solve for a pendulum motion for initial angle 10 degrees. Like we talked about before, is that what I can see is that the motion is simple harmonic motion. And now I can take a look at the phase space plot, and you can notice that here that it looks like a circle. Okay. Okay, again, what I've done is I've just had this at 10 degrees and I made a circle. Okay, and you can see up above that here I'm plotting the simple harmonic motion solution on top of the pendulum solution. However, if I pick an angle of a larger angle where the small angle approximation doesn't work, you can see here that there is an obvious difference between simple harmonic motion and the pendulum solution. And you can see here that the shape, obviously pendulum is periodic, okay, but it's not simple harmonic motion because I can't describe the motion with sines and cosines, harmonic functions. And kind of see this guy's kind of not circular anymore. And, you know, we can get really extreme here. We can say, well, let's make it 170 degrees. And you can see here, whoa, look at that. You know, obviously, this is not a sine function. That's the solution for the pendulum. And you kind of get, again, it gets kind of football shape here. Okay, that I'm showing you there. All right. Now, one problem with the phase space plot is you can't, unless you know the initial conditions, you lose the time information. Remember, these are all times. So you lose time information. So can we still get time information from these types of plots? The answer is yes. So let me show you how we can do that. Okay, so what I'm going to do is show you an animation. And to show this guy, what I have here is, notice what I do is, this is a phase space plot. But what I'm doing is I'm plotting trajectory as a function of time. So basically plotting it as a function of time. So this guy initially starts here, okay, has 0 speed and this initial position there. And I'll let it go. And you can see as this thing kind of goes around, you can see that it makes a circle. And not only do you get the phase space plot, you also get the time dependence of this thing. So it keeps on going around and around and around and around. Okay, so that's really cool. And again, that's for simple harmonic motion. It makes a nice little circle there. Okay, so let's kind of review before we stop. Let's kind of review the really important points of simple harmonic motion. Okay, so again, when do we get simple harmonic motion? We get simple harmonic motion when I have a linear restoring force. And the main result of that is, first of all, I get motion that's periodic, where the period is defined in respect to the natural frequency. I get one period, okay? I don't have multiple periods, okay? Second, the period is independent of initial conditions. The period of the pendulum or the simple harmonic motion doesn't depend on initial speed and position. The motion is described by harmonic functions, sines or cosines, and mechanical energy is conserved. Finally, I'd like to talk about, you know, can motion be periodic but not simple harmonic motion? Well, you know of an example is a simple pendulum. If a simple pendulum, notice that, okay, if I take a pendulum and let it go, it's going to repeat the motion. So obviously it's periodic. But is it simple harmonic motion? Well, for large angles, it's not. Now, why is it periodic? Well, the restoring force for for a pendulum looks like minus mg sine phi. This is a restoring force. It's because it has a minus sign, but it's not so satisfies that condition. But it's not linear. Okay, and so this is a non-linear restoring force. Okay, so the motion is periodic, but it's a non-linear. So what's going to happen is, and we're going to study non-linear periodic motion, okay? What's going to happen is you're going to get periodic motion, but we're going to have to throw out a lot of these things. First of all, there is not going to be, well, there might be one period, or there might be two, or there might be multiple periods associated with the oscillation. We're going to see that for a nonlinear restoring force, that the period is dependent on the initial conditions. The motion cannot be described by harmonic functions, but the mechanical energy is conserved, so that's a nice thing. Okay, so that's my introduction to simple harmonic motion. It's really important stuff. That's why we're doing it. We'll see you later. Take care. Bye-bye.